In yesterday's class, we were discussing graphs, and I explained to you that there are two ways to represent graphs. One is using adjacency matrix, the other is using adjacency list. And then we looked at systematic ways of exploring the graph. So we looked at breadth first search as a way to systematically explore the graph using levels, right? So you start with one node and go level by level. And then we saw that BFS has certain applications, like for example, it can find cycles, it can find out if the graph is connected, you can find odd cycles, which is useful to find out if the graph is bipartite. And BFS generally finds you the shortest path from the source to shortest path in terms of number of edges from a source vertex to any other vertex. Then we went on to DFS, depth first search, which is a slightly more complex or more involved way of exploring the graph, which uses recursion. You don't have to write it using recursion, but it's more convenient to write it using recursion, where you call DFS with a starting node I, and what the DFS will do is it will mark I as visited, then it will call, pick a neighbor of I, call DFS with that neighbor, and it will go on like that. And we saw basically that it is useful to keep track of certain parameters while DFS is exploring the graph. So specifically, we said that we could keep track of keep track of the pre and post values. So the pre value basically is the value. So so you keep track of the pre and post values. So pre I keeps track of the counter. So you remember the counting, you're counting every in and out. So when you enter the DFS, you count, you increase the count, and when you exit DFS, you increase the count, and then you keep track of the count when you enter and you exit. So you have a pre and a post. And then we said basically that the pre-post value, if you take the pre value and the post value, I have indicated pre by green and the post by red, then there is a nice parenthesis structure to this pre-post value. Okay, this is nice parenthesis structure, and in particular we found an application for the pre values at least, and I am going to show you today an application of the post values, but we found an application for the pre values. What did we say? We said we can find out the clusters in the graph by looking at the pre values. How do you find the clusters in the graph? You find the clusters in the graph by using another counter called low. Okay, what does low do? Low keeps track of the lowest pre value that has been encountered in DFS. So it keeps track of the lowest pre value. So when you enter 9, the pre value is 0, then it becomes 1, 2 and so on, and when you come to 8, for example, 8 sees 9. So 8 can see a pre value of 0 because 9 has a pre value of 0. So 8's low value is set to 0. So 4's pre value is set to 0, that everybody's pre value is set to 0. So 9's pre value is also set to 0. So nodes whose low value is equal to its pre value are the roots of these clusters. So 1 has a pre value of 7 and its low value is also 7. So it's a root. Similarly, 9 has a low value and a pre value of 0. So it's a root of the cluster, and he said we can do that. So we found a use for pre values. Alright. Now in today's class, I am going to discuss a use of the post values that we used in the DFS algorithm. So specifically for that, we looked at directed graphs, right? So you take directed graphs and you can apply DFS on directed graphs, and I explained to you that when you do directed graphs, your edges will get classified into different kinds. So the first kind of edge that we will have are these dark edges, which you see on the graph, which is the edge that is formed when you first visit a node, and these dark edges basically make up a tree, right, which is called the DFS tree. And other than that, you will have edges which basically point backward like this, from a descendant to a parent. Such an edge which goes from a descendant to a parent is called a backward edge. And then you can have edges which go from a node to a descendant node. How did you get this kind of edge, node to descendant node? Because the graph is directed. So what can happen is DFS visits 9, then 6, 7, 5, 4, 8, but from 8 it cannot reach 9 because the edge is pointing downward. So 9 is not a neighbor of 8, but 8 is a neighbor of 9. Alright, in directed graphs that's possible. So therefore from 8 you don't actually go to 9, and you go from 8 to 4, you go back like this, go like this, and then you go back this way and you go to 9, and then when you come to 9 you are exploring another edge of 9 and you come to 8. So that is how you get this forward edge, okay. So in a directed graph you can get backward dotted edges, you can get forward dotted edges, and you can also get these funny kinds of edges which are called sideward or cross edges, okay, sideward or cross edges. So you are having an edge, so you visited 7, 6, 5, 4, 8, went back to 9, went to 10, and then 10 has a neighbor which is 7. Now the reason why from 7 you didn't get to 10 is because this arrow is pointing from 10 to 7, therefore 10 is not a neighbor of 7, but 7 is a neighbor of 10, which is why you did not go to 10 from 7. So when you went back like this and from 10 you came to 7, so 7 was already visited, so you get this cross edge. So you get these three kinds of edges: forward dotted edges, backward dotted edges, and cross dotted edges, and you can do most of your analysis of the DFS structure by analyzing these kinds of edges, right, three kinds of edges. We will see in the problem today. When we get to the problem we will see how to do the analysis. Okay, so I am going to take yet another application of DFS in graphs which are called acyclic directed graphs. Now a graph is directed and cyclic if there is a directed cycle in the graph, that is there is a path from U back to U going through other nodes. So you can go from U to V to W to X and then come back to U, okay. So there is a directed path going around from U and coming back to U, that is called a simple cycle inside a directed graph. A graph is called acyclic if it does not have these directed cycles, okay. Now whenever a graph is acyclic, that means it does not have any cycles, it comes to mind that I must be able to arrange the nodes of the graph in some order, okay. I must be able to put the nodes on a line so that nodes which are later, right, you know, the earlier nodes will only have edges pointing to the later nodes. There are no edges pointing from later nodes in the line to earlier nodes in the line. So I must be able to arrange the nodes in the line in such a way that all the edges go only from earlier nodes to later nodes. Such a writing of the nodes on a line, which means ordering of the nodes as a linear order, is called a topological sort, okay. It is called a topological sort. It is called topological because you are sorting a graph. A graph is a kind of a topological object, right. It's a kind of a, visually you can see it's like a object in space, right. So it's basically got some dimension element to it, that's why it's called topological. But when you sort it, you're ordering the nodes. Why do you want to sort the sort or topologically sort the nodes of a graph? This has applications in many areas. Like for example, imagine that you are creating a VLSI circuit and you have drawn the data path, which means that you have drawn all the nodes which do computation and you draw where these computations are used. So you get a graph. This graph will be acyclic, and then you can ask yourself, this acyclic graph, the reason it's acyclic is because if you connect the output of the last element back to the beginning, then the whole thing will simply cycle. It will become a combinational circuit which will loop, right. So that's why it's acyclic, and only way you will allow the node in a data path to feed back to the first node in a data path is via a counter, via a register, right, via a clocked element. So this acyclic graph I want to topologically sort basically because then I can order the way in which these nodes will execute. So if I want to convert these into, if I want to do instructions or something like that, I can make these things execute one or the other. So in any similarly I can do in compilers also. If I have expressions basically represent a kind of a data flow, and I can order the way in which this expression is evaluated by doing a topological sort of the expression graph, okay. Expression graphs are directed acyclic graphs, so I can basically do topological sort of it, which will tell me what order I want to execute it. So there are many applications of topological sorting, and so this graph here is an acyclic graph. As you can see, there are no cycles in this graph, and I'm asking, can I find a topological sort, an order of this graph in such a way basically that the earlier nodes will have edges to the later nodes, but later nodes will not have any edges to the earlier nodes. That's what I want to do. And it turns out that topological sorting can be done very easily by using depth first search. So here for example, this 5 to 7, so I am taking all the nodes which have no incoming arcs, so it makes sense, right. 5 to 5, actually 2 it is wrong, okay. I should do 5, 7, 3, right, 5, 7, 3 first because they have no incoming arcs. After that I should take 10, 8, then I can take 11, then I can 9, then I can take 2, right. So the reason why this 5, what I have written here is not a topological sort is because 2 is appearing before 11, whereas 11 is got an edge to 2. So this is not a topological sort, okay, this one over here. So if 2 are sitting at the end, it would be a topological sort, okay. So how do you find a topological sort using DFS? This is a question we are asking. So here is an example of a graph which is cyclic. It has got cycles in it, and because this is cyclic, you cannot do a topological sort on it, right? There is no way to topologically sort a graph which has cycles because 9 has to be before 10 and 10 has to be before 9. You cannot satisfy both those conditions. So you have to remove the cycles from this graph. So let's say I remove all the edges which form cycles in this graph. Now I have got a graph, right? Of course, this edge also has to be dropped, right? This edge also has to be dropped. So if I remove all the cycles in this graph, then I can ask myself whether I can do a topologically sort of this graph. And the answer is you can do it by looking at a depth first search of the graph and identifying the post values. So you see when you do a depth first search of the graph, you get these post values. Even though I have removed some dotted edges, it doesn't really change the pre and post values of any of the nodes, right. Even if I remove all the dotted edges in this graph, the pre and post values will remain the same, but because you remember the pre and post values really are coming from the DFS tree, which is the solid edges in the graph, okay. So the order in which the nodes are visited. So the pre and post values, so you see a very interesting property here that the post values, so for 9 for example the post value is 19, for 10 the post value is 18, for 6 the post value is 16 and so on. So you can see that in some sense if I look at the post values in decreasing order 19, 18, 16, 15, 14, 13, 12, 11, 10, 6, then the decreasing order of post values will automatically result in a topological sort of the graph. So 19 gives 9, 18 gives 10, 16 gives 6, so 10, 6, 7, 5, 4, then 1, 2, 3, then 8 is a topological sort of the graph, okay. So a very simple way to do topological sorting of the graph is to do a DFS traversal of the graph, keep track of the pre and post values, right, as we did last time, then list out all the nodes according to the decreasing order of the post values, list out all the nodes in the decreasing order of post values, and that listing of the graph by decreasing order of post values will be automatically a topological sort of the graph. To go a little bit traversal, BFS and DFS traversal, we have spent some time discussing it. I want to go beyond it and look at two different kinds of algorithmic techniques that we can do on graphs. Of course, there are many different algorithmic techniques that can apply on graphs, but I am going to discuss two today. One is greedy method and the other is dynamic programming method, and in the Thursday's class we will be discussing the network flow method. Three different kinds of algorithmic techniques that we can apply on graphs, okay. So I will be looking at greedy and dynamic programming, DD and dynamic programming methods, okay. So now in order to discuss these things, I am going to introduce to you a slight extension to what we have discussed so far on graphs, which is what is called a weighted graph, okay. So far we have had graphs with nodes and edges. We labeled the node sometimes, which means that we actually when we visited a node we marked it visited. We kept track of some counters, right, for every node. We said there will be a pre counter, a post counter and so on. But now I am going to do something with the edges. So for every edge I am going to associate with that edge a weight of the edge, also called sometimes the cost of the edge, okay, weight or a cost of the edge. So we associate with each edge a real number, okay, need not be an integer, a real number. The real number can have value which is 0, can have positive, negative, any value. So that number is called W of E for the edge E. And if you have a sequence of edges which form a path. So from V1 to Vn plus 1 you have a path V1, V2, V2, V3, V4, V4 made out of edges E1, E2 and so on up to En. Then the cost of the path or the weight of the path, okay, cost or weight of the path is given by summing up the weight of the edges on the path. Okay, so you can have a sequence of edges, you can add the weights of all the edges and you get the weight of the path. And now we are asking the question, what is the shortest weight path? So if you remember, we basically drew a diagram of airline cities and airline routes from one city to another and so on, and we asked the question, what is the shortest path in terms of number of edges? That problem basically models number of hops. They are saying I want to do the minimum number of flight changes while going from Chennai to Varanasi. But I could ask the question, what is the minimum fare that I want to find the shortest path from Chennai to Varanasi in terms of how much I will spend, right? So then I can have for Chennai to Bombay, there is a fare, from Bombay to Delhi there is a fare, Delhi to Varanasi there is a fare, and I ask, is this the cheapest way of going from Chennai to Varanasi, or maybe there is a way to go from Chennai to Kolkata, Kolkata to Varanasi that is cheaper because the fare might be cheaper, okay. So it is not necessary that the shortest path in terms of number of edges is the shortest path in terms of some other metric, which could be like, for example, fare, the price that I pay for the ticket, or time taken. For example, I might find that the time taken to go from Chennai to Varanasi via Bombay is much more than the time taken to go via some other city, right? So you might look at time as the thing that you're optimizing. So each of these things, what we are doing is setting with each edge a weight function depending on whatever your application is, and then we are defining the cost of the path as the sum of the weights of the edges. And what we are interested in finding out is the minimum weight path or the minimum cost path, which is the shortest path in terms of sum of the weights of the edges. Now in order to do this, first we have to ask ourselves, before you start looking at new algorithms for any problem, you always have to ask yourself whether existing algorithm will work or not. So I ask, if you know a few techniques, you should see, can I use the existing technique, the technique I already know. So can I use BFS to find the shortest path? This is the first question I have to ask, and the answer is, unfortunately it can't be used. It will not find the shortest path. Here I will give you an example of this. So here I made a graph which is made of these 7 nodes. So you can see basically that the shortest path in terms of number of edges between 1 and 3 is actually the directly you can go from 1 to 3 because it is connected by an edge. That is the shortest path in terms of number of edges, 1 to 3. But I have labeled all these edges with weights. So you can see these are the weights that have been written over here. So the shortest path from 1 to 3 in terms of weights, right, in terms of cost of path, is not the edge directly going from 1 to 3 because this costs me 80. Okay, it may be a very expensive flight to go directly from 1 to 3. Whereas if I go via 2, that means if I go 1 to 2 and then take 2 to 3, then the total weight or total cost is 10 plus 6, which is 16. So there is a shorter path via 2 to 3 in terms of weight than to go directly, alright. So which is why BFS, breadth first search, which looks at level by level exploration of the graph, will not return to you the shortest path when we look at it in terms of weights, okay. BFS is not going to do it for us. So if BFS is not going to find the shortest path, what algorithm can we use? That is a question they are asking, and therefore we look for another alternative algorithm. Now it looks something like BFS we need, right, something like BFS. It has to go, instead of going level by level, which is distance in terms of number of edges, you are trying to do something like level by level, but distance not in terms of edges, but distance in terms of cost or weight, sum of the weight so far. Something like that is what we want to do. So can we modify in some sense this BFS algorithm to take into account these weights that we have put on the edges? So what we do is that we maintain a vector for every node called distance I vector. What is this vector going to maintain? It maintains the shortest path found so far to the node I, okay. Just like visited I tells you whether the node I is visited or not, shortest distance I tells you the shortest path that we have found so far to the node I in the algorithm, okay. At each step what we do basically is that we look at whether or not there is a need to update distance I. If you have found a shorter path to I than whatever you have found so far, then you will update the value of distance I. So keep on updating distance I as you find shorter and shorter paths, and after you have looked enough at the graph, at all the paths in the graph, eventually you will find the right distance for every node I. Okay, that is the way the algorithm can work. So simple greedy algorithm would work like this. Greedy algorithm. Greedy means what? Greedy means a greedy algorithm tries to take local optimal solutions. It looks at the neighborhood and tries to find a local optimum at a given point in time. Okay, tries to optimize locally, and each local optimum that it does, if it picks a node and finds an optimum for that node, once it has found a local optimum, it will never visit that node again. So the greedy algorithm has two properties. One is it uses only local properties to proceed, and second property it has basically is that once it visits a node, that is once it has identified an optimal value for the node, it will not backtrack, it will not come back to that node and try to do something better for that node. Okay, it will leave that node alone and go forward. Such an algorithm is called a greedy algorithm. Okay, so not all problems the greedy algorithm will find the best solution for you. Greedy algorithm you can always write for every problem, but the greedy algorithm will not find the optimal solution for that problem in all cases. But there are many problems for which greedy algorithm will always find for you a good solution, optimal solution. In this particular kind of problem that we have, which is the shortest path problem, the greedy algorithm will return for you the best solution. Okay, it will always return for you the best solution, so which is nice. So what we do in this greedy algorithm basically is that just like in BFS and DFS, we mark, when we look at a node, we mark it as visited. Initially basically we set visited to false for all the nodes, and we set the distance that have been found to that node as infinity. So we are going to keep reducing the distance. So we are starting with infinity and keep finding shorter and shorter paths to the node. Okay, start with node S. So therefore you are going to mark visited of S as 1, and you are going to mark distance of S as 0, because the path from S to the cost to go from S to S is obviously going to be 0. Okay, so for each node which has not been visited, choose a node U that has not been visited. Okay, an unvisited node. That is what they are saying. Choose U so that visited U equal to false, and such that the distance of U is minimum. So clearly in the beginning, since only S has got 0, all the others have infinity, this part, this choice will have visited, S is not yet visited. Okay, so this choice is going to pick up S in the beginning, right, because distance of S is 0, it is minimum, and S is not visited, so it is going to pick it. Later on you might pick other nodes, but in the beginning it will pick S. Okay, and what you will do is you will mark visited U equal to true. So you are going to mark visited of S is equal to true. Then what you do basically is, once you have marked a node as visited, you are going to take all its neighbors and update the distance to the neighbors. So for each neighbor of U, mark the neighbor as visited. Each neighbor of U that has not been visited, right, visited V equal to false means that has not been visited, right. Why are we doing this which has not been visited? The reason we are doing it is because, remember, in a greedy algorithm, once we have visited a node, we don't want to visit the node again. Once you are done with a node, we don't want to do anything further with that node. So all the nodes that are visited, we are assuming we have found the best path to them already, so we don't want to visit them again. So that's why we are picking only those nodes which we have not visited already, and for those distances we are checking whether or not the distance can be improved, right. How are you checking whether the distance can be improved? If the distance that you have already found to V is greater than the distance that you will get by going via U, distance to U is the distance up to U, and weight of UV is the cost of the edge from U to V. So distance U plus weight UV basically is consisting of the path which goes to U, and then via U it goes to V. So you are saying, if I have found a path to V and that one's distance is distance V, and if I have a path, if I calculate the weight of the path via U and I find that the path via U is shorter path, then basically you replace that path with the shorter path. So that's why you are saying replace distance V by distance U plus weight of U. Is that okay? Okay, very simple. Extremely simple greedy algorithm. I can see that you can fit this algorithm in one page. Okay, pseudo code you should write in one page. If you can't write in one page, it basically means that you will make mistakes, because if you have to flip pages, okay, I have written something here, I have written something here, you go back and forth, you are going to make many mistakes in your algorithm and your algorithm will not be good. You should try to write, use abstract subroutines or whatever it is, and try to write the pseudo code for every program in one page so that you can see everything. Keep staring at it and make sure that your code is correct. Okay, so this is one page pseudo code for greedy algorithm or finding shortest path. Okay, how often do you do this? You repeat this n times. Note that, specifically note, we are not using I anywhere in this loop. Unlike in all the other things that we had, we are not using I anywhere, which means that this I is used only to count n times. You got to repeat n times, doesn't matter. Okay, so you are going to repeat this process n times. What process you are repeating n times? Pick a node that has not been visited so far, right, and whose distance is minimum, and update the neighbors, distance of the neighbors of this node. This process you are going to repeat n times. Okay, and the greedy algorithm, if repeated like that n times, will always find for you the shortest path. Okay, this algorithm was invented in the 1950s by Dijkstra, one of the most famous computer scientists, and that is why it is also called Dijkstra's algorithm, right. So what is it doing? It is doing a very simple thing. It is dividing at any given point in time. The greedy algorithm is dividing, or Dijkstra's algorithm is dividing basically the set of nodes into two sets: the visited nodes, the unvisited nodes. Visited nodes are nodes that you do not want to visit again, which means that you have already found the shortest path to those nodes. Okay, you already found. Unvisited nodes you are not sure about, that is why you have kept it as unvisited. At any given point in time, what do? You pick from the unvisited vertices, you pick a vertex u. Which vertex do you pick? You pick that vertex u which has the least distance value written on it. Okay, the least distance value written on it. Pick such a node. So this is being done, therefore that is why it is called greedy, right. It is greedy for two reasons. Because you are doing locally, you are picking the node which has the least distance value written on it. You are not looking at some complex optimization, just picking the least distance value and that is it. That is why it is, and once you have picked a node, you are going to mark it as visited, and once it is visited, you are not going to come back to that node again. Okay, this is the reason why this algorithm is greedy algorithm. Okay, so why does this work? It works because you have picked the least. Assume for a moment, by induction I can show you that this algorithm will work, because assume by induction that all the nodes inside this set visited, you have already found the shortest path to. Okay, you have found. Okay, assume. So for in the beginning only S is there, so the shortest path to S is just S itself. So it is obviously true in the beginning. So base case is true. So by induction, assume that it is true for all the visited vertices. I am going to show that it will be true when you add U to the list of visited vertices. Why is it true? It is true because you have picked U, which is the lowest among all distance values for all the unvisited vertices. Among all unvisited vertices, U has the lowest distance value. Therefore, if there is another path to U which is shorter than just going directly to U, then that path basically has to go through some other vertex. Let's assume there is a W. So I go from here to W, and from W I come to U. That path is going to be longer than this path always, because W has a distance value which is greater than that of U, because U is the least distance value. So therefore I can be sure that by picking the node with the least distance value, right, I am finding the shortest distance to U, and because I found the shortest distance to U, I can now include U in the list of visited vertices. Alright, so I make U also as visited. So I increase the set of visited vertices by adding U to it. Okay, and then what do? I do this distance update for all neighbors of U. Let's say V is a neighbor of U, right, and I am not looking at visited. So you may have a neighbor which is W, which is sitting inside visited vertices. I am not going to update the distance of that. Why is that? I do not need to do that. The list of visited vertices I have already found the shortest path, so I do not need to go there. Okay, so therefore I only take the list of unvisited vertices which are neighbors of U. Let's say V is let's say a neighbor of U which is an unvisited vertex. I update its distance if necessary. What does it mean? I have a path already found to V which is of length distance V. I check whether the path via U, the distance U plus weight of UV, is less than the path that I have already found to V. If it is, then I update the distance value of V so that it is equal to the distance of this path via U. This is what I do. So this algorithm, Dijkstra's algorithm, greedy algorithm, is going to work. It's correct. It's going to work always, and it's going to be efficient because you are only visiting nodes once, right? Remember, every node is visited exactly once, right? Every node is visited only once. Once visited, it's going to be marked as visited, and you are not going to come back to it again. Okay. So, so what is the complexity of this algorithm? There are 3 steps in Dijkstra's algorithm. So your first step basically is selecting an unvisited vertex U which has the least distance value. That is the first step. Second step in the algorithm is to remove U from the list of unlisted vertices. Okay, that is the second step. Third step basically is to access all the neighbors of U and update the distance values of the neighbors. Right. Now clearly, if you update the distance values of the neighbors of U, then because you are updating the distance values, the shortest, the node with the lowest distance value written on it is going to change, isn't it? So this update step will impact this first step, select step. So once you do this update, you may find a different node which has the shortest distance. Remember that, okay? So it's not that I can sort the unvisited nodes by order of distance and then I can keep selecting. That is not what greedy algorithm is doing. It's picking the lowest distance value, and after that it's doing update. When you do the update, the whole list of unvisited vertices is going to, the distance values of all of them is going to get changed. So again you have to pick the lowest distance value, again do an update, again the values of all this distance values of all the unvisited vertices is going to change. Okay. So every time I do an update, the values of distance is changing, so the first step is selected. So what is the complexity of this? So you can see that selecting an unvisited vertex U with least distance requires basically that if you have an adjacency array, this could take order n time, right? Because you find min of a list of n takes n time, right? And then you're going to repeat this n times, right? You're going to repeat this whole thing n times. Remember Dijkstra's algorithm, you're repeating it n times. You go n times, you're doing this update step visit. So n multiplied by n gives you n square. Okay. So the total number of total complexity of just the first step is order n square. Okay, I can count in many ways. I'm just counting how many times I'm doing overall first step, how many times overall I'm doing second step, how many times overall I'm doing third step, and I'm adding the 3. So number of times I do the first step basically is n times I have to do order n operations to find the min each time, and I have to do n times this operation because for every node I have to do it, I have to do this. Therefore, totally n square times I will do the first step. Second step, I have to remove U from the list of unvisited vertices. Okay, so to remove U from the list of unlisted vertices is unvisited vertices is not difficult. It can be just order 1 operation, right? It can be just an order 1 operation. So for n steps, this could be order n. Okay, because if you are keeping a visited I equal to 0 or visited I equal to 1, removing U from list of unvisited vertices, just marking U as visited. So I just have to set visited U equal to 1. So that's a single step, the constant time operation. That's why order 1. And since I have to do the n times for n nodes, therefore order n. Okay, accessing all neighbors of U and updating the distance values, right? So now again, just like BFS and DFS, you notice in Dijkstra's algorithm also, every edge will be visited exactly twice. If UV is an edge, you will visit this edge when you come from U to V, and you will visit the same edge again when you come from V to U. That's only 2 times you will visit every edge. Okay, because remember, okay, so therefore since every edge is visited only 2 times, therefore the number of times that you will do this third step is order m. So the total complexity is order n square plus order n plus order m, and since order n is less than order n square, order m is less than order n square, the algorithm complexity is order n square. Is it clear? So the overall complexity of Dijkstra's algorithm is order n square. Question we can ask ourselves is, can we do better than this? Can we do better than order n square? Okay, because order n square, shortest path, imagine for example that you are trying to find in a telecommunication network the shortest route. So there could be a very large number of routers in telecommunication. The world's number of routers in the world might be easily in hundreds of thousands, right? And you want to find the shortest path. So order n square can be 100, 10 to the 5 into 10 to the 5 is 10 to the 10, very large. So if I can do in order n log n, that will be 10 to the 5 multiplied by log of 10 to the 5, much smaller number, isn't it? It will be order of 10 to the 5 multiplied by some 5 into something, right? So it will be 50,000 steps. Suddenly you will find yourself coming down very small number in between. So we want to do if possible in order n log n. How do you do it in order n log n? Right, I am not discussing this data structure called a heap because this I guess you have studied already in some earlier part of the course. If not, you can read about heaps. Heap is a data structure which is a binary tree, okay, it's a binary tree like this, and the binary tree in a heap is kept balanced, which means that the height of this binary tree will always be log n, where n is the number of nodes in the binary tree, okay, and it will be kept balanced, but it's not a complete binary, it's not a normal binary tree in the sense that the left side of the binary tree is always less than the root and the right side is greater than the binary root. That's how the normal binary search trees are represented. This is not a binary search tree, this is a heap. In a heap, all that we want is that from a node, as you go up the heap, the key values should decrease. So here 15 is the key value, 7 is the key value, 5. So as I go up from a node in the heap, the key values that you're storing on the node should keep decreasing. So heap is a data structure which is a binary tree, has a root, it is kept balanced, and it has this property that as you go up from a node, the key values keep decreasing. Such a data structure is called a heap. If you have read about heaps, that's good. If you have not read about heaps, I'll encourage you to go read about it, or you will study it in the class later on somewhere, okay. So the interesting thing about a heap basically is that insert operation in a heap takes order log n time, delete operation of a node in a heap takes order log n time, and finding the minimum in a heap is order 1 time, it's constant time, because you just have to find the root of the heap, right. This is the minimum. Minimum is always in a minimum heap, the top of the heap will be minimum. In the maximum heap, the top of the heap will be maximum. We want to maintain a minimum heap. So by using a minimum heap, we can do minimum finding in constant time, and the deletion operation we can do in order log n time, right. Removing u from the list of unvisited vertices can be done in order log n time, and doing a distance update. Basically, when you do a distance update, what happens? Each time you do a distance update, you are changing the key values on the heap, right. So changing the key value of a node on the heap is equal to basically deleting that node and replacing that node with a new node. So you are doing one delete and one insert operation. So since, right, every distance update will change the key value, and because you are changing the key value is distance value, right, because you are changing the distance value which is the key value of the node, therefore to change the key value you have to delete that node from the heap and insert another node with a new key value into the heap, okay. So you are doing one delete, one insert operation. Both of these are log n, which is why for each distance update that you do, that means for each edge, each neighbor you are doing a distance update, each of them you are taking order log n time, and since there are potentially m neighbor visits you will do overall in the graph, right, because every edge you will visit is a neighbor visit. So you will do overall m neighbor visits, and for each neighbor visit you are doing log n time operations. Therefore you get order m log n complexity for the third step. For the first step you get n log n, for the second step you get n log n, but for the third step you will get m log n, okay. I'm sorry, for the first step you get now order n time, because finding the minimum is order 1 time in a heap, and since you are doing that n times, it's order n. So the first step is order n, second step is order n log n, and the third step is m log n. Therefore the total complexity of the algorithm, Dijkstra's algorithm, greedy algorithm, in which we use heap data structure, is order m plus n log n, and which typically, if m is small, right, if m is small, may not be, if m is small, that is if m is of the size of order n, then order n log n you will get, but m may not be small, okay. If m is not small, m is very large, it means m is like n square, then this is actually even worse than doing without heap, because this is n square log n, whereas we had found already an order n square algorithm, right, without using heaps. So if m is very large, then it's simply better not to use heaps, use the standard adjacency list and do whatever we did earlier, okay. But if m is very small, you can use this algorithm and it becomes this thing. Most of the graphs which we encounter in real life, m will be typically small, it will be of order of n, okay, it won't be order of n square. So having discussed that, I want to move on to a variation of that problem in which I am going to add to the graph negative weight. Now I did not tell you actually that the graph that we considered for Dijkstra's algorithm has no negative weight. I didn't tell you that, okay. But Dijkstra's algorithm will not work if the graph has edges with negative weights on it. It will only work if the graph has edges with positive weights on it. Alright. So if the graph has edges with negative weights, then we need to do something other than Dijkstra's algorithm. Right. So greedy algorithm is not going to work. We have to use something else. We are going to discuss dynamic programming as a method to use. Right. Why does Dijkstra's algorithm not work? Firstly, let's look at graphs with negative edges, right. For example, like this is a undirected graph and I put a negative edge of -6 here. You can see that this graph is pathological. Why is it pathological? Because I can go from 3 to 2 and that will reduce the cost by -6. I can go back from 2 to 3, it reduced the cost by another -6, so it became -12. So I can do 3, 2, 3, 2, 3 like this, I can keep going around like this. And the weight cost will keep reducing by -6, -6, -6, I can keep reducing. So I can reduce the cost to anything I want, right. I can make it negative value, any negative value I want by just going around 3, 2. So if I want to go from 1 to 5 rather than doing 1, 2, 5 which is 8 plus 20, 28, I will go 1, 2, 3, 2, 3, 2, 3, 2, 3 many times, then it will do 8, and then if I do this 100 times it became -600. So 8 minus 600 is -500 and whatever it is 92. Then I go like this 20, so I got -592 plus 20, which is silly, okay. So this whole thing is meaningless. That is why you don't consider undirected graphs with negative edges, because it's pathological, okay. It doesn't make sense to consider undirected graphs with negative edges. So you only consider directed graphs with negative edges, alright. So here is a directed graph with negative, but here in this graph what I have done is I have put -20 on this edge, okay. Now what has happened, because I put -20 on this edge, is I get what is called a negative cycle here, even though it's a directed graph. So I can't do 3, 2, 3 because there is no 2, 3 now. I can only do 3, 2, but here I can do 5, 6, 7, 5, 6, 7, 5, 6, 7. So each time I do 5, 6, 7, -20 plus 5 plus 10. So -20 plus 5 plus 10 is -5. So I can go from 5 around this loop and come back to 5 and I have reduced the cost by 5. If I do it 2 times, reduce cost by 10. I can go 10 times, it will reduce the cost by 50. Again pathological, meaningless, okay, which is why you consider for negative edges, you only consider graphs which are directed and which don't have negative cycle. What is a negative cycle? Negative cycle is something like this, a cycle in which the sum of the weights or the edges of that cycle is negative. That's called a negative cycle. So a graph which has no negative cycles and which is directed are the only graphs that we will consider. That's the only meaningful graph, okay. So such a graph. So this graph for example has no negative cycles because I reduced -20 to -10. So you can see if I go around the cycle now, 10 plus 5, 15 minus 10 is 5. So the weight is positive, okay. So no negative cycles in this graph. Now I can ask myself, can I use Dijkstra's algorithm or a greedy algorithm to find the shortest path from source, which is 0, this is the source node 1 to all the other nodes in the graph? The answer is you cannot. Why not? You cannot because what does Dijkstra's algorithm do? Dijkstra's algorithm will pick at any given point in time the node with the from the unvisited nodes, it will pick the node with the shortest distance. So initially it will start with this node 0 and then it will update the distance value of its neighbors. So it will say, okay, let me update the distance value of the neighbors. So it updated 2 with 8 and updated 3 with 10. I have written the distance value next to the node, okay. It did. After it did this, what will Dijkstra do? It will say it will pick the node with the shortest distance value. 8 is the node with the shortest, all other nodes remember are infinity. These nodes are all infinity and it did not pick 1 because it is visited already. It has to pick an unvisited node with the shortest distance value, that is 2, right, which has 8. So it will pick 2 and after it has picked 2, it will mark 2 as visited, okay. When it marks 2 as visited, it means it is not going to visit 2 again. It will mark 2 as visited and then it will start exploring the value of the neighbors of 2. It will start exploring the distance of, it will start updating the distances of the neighbors of 2. It will update the distance of 5 for example and so on. This is how it works. But in this graph we can see very clearly that there is a shorter path to 2 via 3. I could have gone to 1 to 3 to 2 because of this negative edge here. 1 to 3 will be of weight 10, but when I do 3 to 2 it has minus 6, so 10 minus 6 4. So there is a shorter path of weight 4 or cost 4 going via 3 from 1 to 2. Dijkstra did not find it, it found 2 initially, right, so it stopped. So problem with Dijkstra is that once it has visited 2, it's a greedy algorithm, so once it has visited 2 it's not going to visit 2 again, and because it's not going to visit 2 again, it's not going to discover this new path via 3. Okay, it's not going to discover, and therefore Dijkstra does not find the shortest path in graphs which have negative edge weights. So what do I do? First question I can ask is, why don't I just modify? See, if I have a algorithm, I should try to use that algorithm as I explained to you. I know that greedy algorithm, Dijkstra's algorithm works, at least it works for graphs with positive edge weights. So can I convert my graph which has negative edge weights into another graph which has positive edge weights? Can I do that? So one trick I can try is, let me just simply add, since minus 10 is the weight here, so I add 11 to every edge. If I add 11 to every edge, all the weights will become positive. Then I can apply Dijkstra. Will that work? Okay, this is the question I have in my mind. Will that work? What do you think? Will it work? If I add 11 to all the edges, right? So everything becomes positive. Then I apply Dijkstra. Will that work? Because if I add 11, everything has become positive. So now you can do Dijkstra, no? So then why are we worried about dynamic programming? Simple greedy algorithm should work, right? Will this work? Anybody wants to take a shot at it? So I have added, okay. So now this is a graph which has no negative edges. We added 11 to everything. So you should apply Dijkstra on this, no? So people are saying yes. So does yes. So CBIT is saying yes. Does it mean that it will work? So you think that it will work? Dijkstra's will work on this. Will it find the shortest path? No, you remember that it will find. Of course, it will find shortest path in this. But is this the shortest path in the original graph? Okay, is this the shortest path in the original graph? That's the question we are asking. Okay. All right. So let me answer this question because I'm not hearing it from any of you. So let me answer this question myself. It's not going to work. Okay, it's not going to work. Why won't it work? Because look, for example, now we know that the shortest path from 1 to 2 is 1, 3, 2. But here actually this is not going to find the shortest path as 1, 3, 2. Why is not going to find? Because 21 plus 5, 26 is greater than 19. So it's going to actually say that the shortest path again is 1, 2. It's not going to find 1, 3, 2. So adding, why did it work? It didn't work because this one you added 11 to this edge, you added 11 to this edge, actually added 22 to this path, whereas you added only 11 to this path. So this was a shorter path, but since you added 22 to it, it became longer now suddenly. Now the problem with adding some number to all the edges is that you are suddenly making the problem change the problem. Remember that breadth first search looks at shortest path in terms of number of edges. Here we are trying to find the shortest path in terms of sum of weights. But by adding some number to all the edges, you are trying to move it closer to number of edges again, right? So if I add, for example, very large number to all the edges, the problem will become like breadth first search again. You are trying to find the path to the shortest number of edges. So this is not going to work. Okay, so it's not working, which is why you need a new algorithm. Okay, so before you start working on a new algorithm, okay, all right, sir, please tell the value is increased by you is always 11, or is there some logic behind it? Okay, so the reason I added 11, it need not be 11, it could be anything else. I added 11 because I wanted to make it at least 0. I could have added 10 for example, and then this would have become 0. I could have added 11, I can add 12 also, I can add any number so long as all the weights become positive. Since the largest negative number here is minus 10, or the highest, the least number here is minus 10, I added 11 so that this can become 1 and becomes positive. Okay, that is the reason I added 11. But you can add any number so long as all the edges have positive weight. Okay. Now, so this doesn't work, alright. So this doesn't work, so therefore I need a new algorithm. So before you start looking at new algorithms, check whether your existing algorithm can be tweaked, modified, make a variant of it and see whether it works, okay. In this case none of the variants work, so therefore I have to find a new algorithm. So the algorithm I am going to discuss is called Bellman-Ford, okay. Now Bellman, for those of you who like to know about history of various things, like Dijkstra also did all his work in algorithms in 1950s, and he is the inventor of this method called dynamic programming. He invented dynamic programming. Now why dynamic programming is called dynamic programming is not very clearly known, but in those days programming meant something else. It meant optimization. When programming, people said programming, it meant not writing program. Okay, when people said programming, it meant doing an optimization, like linear programming. Okay, means set of constraints are there and you want to optimize a function, linear function given a set of constraints, linear constraints. Such a problem is called a linear programming problem. Okay, so integer programming, linear programming. So operations research people were doing a lot of optimization problems, and those problems were all called programming problems. Is that okay? So dynamic programming basically means that you are not doing set of constraints which are static. You want to take a set of constraints which are if then else in them. So you, instead of just writing some linear constraints, you want to write some constraints which says if this were the case then this constraint, that were the case and that constraint. So it's dynamic. So when you have situation like that, how do you solve? And that is the thing that Bellman looked at, and he called that dynamic programming. Is it okay? So that word stuck, and today we are calling dynamic programming whatever he invented. So we are going to use dynamic programming here. Okay, I am not going to discuss dynamic programming because it forms a very substantial part, I understand, of your course. You will learn more about it later, but you will see how it is being used to solve this particular problem. Okay. So what does dynamic programming do? Just like greedy, what it does is it picks the locally best solution. It's greedily choosing the least value of something, and then once it visits that node, it never visits it again. Once it visits something, once it does something, it doesn't come back to that thing again. Dynamic programming on the other hand doesn't have that kind of restriction. You are not saying that once I visited a sub problem or one node or whatever, I am not going to come back to it again. I will come back to it again and again, but when I come back to it again and again, I will remember that I have come back to it again. I will use the solution I have found already for that. So what dynamic programming does, it breaks a problem, just like it breaks a problem down into sub problems. Okay, these sub problems may overlap. Overlap means that problem A and problem B I break it down into. Problem A may involve problem B again. Okay, problem A might involve problem B and problem C. Fibonacci is a great example where we can use dynamic programming. So Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Calculate n minus 1, I have to do n minus 2 plus n minus 3. So n is broken into n minus 1 and n minus 2. N minus 1 is broken into n minus 2 and n minus 2. So when you do n minus 1, you visit n minus 2 again. Okay. So basically you break a problem down into sub problems. Usually you will break it down and write it using recursion. These sub problems may be visited again and again. So in order to not do the sub problem again and again, you remember it. Remember the solution. This is called memoization. Okay, remembering the solution is called memoization. So by using recursion to break the sub problem into sub problems and using memoization or reuse, right, to remember the solution, that method is called dynamic programming. Nothing else, very simple. Okay, recursion plus reuse is dynamic programming. Very simple to remember. Okay, so here what are we trying to do? We are trying to solve the problem, find the shortest path from the source S to any vertex of the graph T. So in order to solve this problem in dynamic programming form, you have to ask what are the sub problems. Okay, so let me write the sub problems as sub problem K. I am defining the sub problem. This hardest part in dynamic programming is choose the sub problem carefully. Sub problem K is defined as find the shortest path from source S to vertex T which has at most K edges. I am defining it like this. Okay, so sub problem is defined as kth sub problem is defined as finding the shortest path from S to T using at most K edges. At most, this can use K minus 1, K minus 2 edges also. At most K, okay, but can't use K plus 1 edges. So if you want to use K plus 1 edges, you have to go to the sub problem K plus 1. Is that okay? So clearly, in order to do this, you need only look at values of K up to n, right? Because there are no simple paths that have more than n edges. In fact, I don't have to do more than n minus 1. The largest length of a simple path is going to be n minus 1. So I need only do up to n minus 1 actually. So there are only n order n sub problems. How is the problem related to the sub problem? Shortest path from S to T is simply the minimum of all the n sub problems. Is that clear? The shortest path from S to T is either the shortest path from S to T with 0 edges, or the shortest path from S to T with 1 edge, or the shortest path from S to T with 2 edges or 3 edges or 4 edges. Like that I can keep doing. Take the minimum of all the shortest paths and that will be the shortest overall shortest path. So very easy to construct a solution if I could do the solution of these sub problems. So how do I do dynamic programming on this particular example? So I found the shortest path from 1 to 2 with one edge. Dijkstra finds it for me. 1 to 2 with one edge, right? With Dijkstra itself, with greedy itself I found it. 1 to 2 with two edges, shortest path, basically at most two edges, remember. So I have two ways of going from 1 to 2 with at most two edges. One is directly, which has weight 8, and another is via 3, which has weight 4. So the shortest path with at most two edges between 1 and 2 has weight 4. Okay. So the subproblem 1, which means one edge, will return the value as 8. Subproblem 2, which has two edges, at most two edges, will return the distance value as 4. So since I am going to take the minimum of the two, I will take 4 and I get the answer. Is that okay? So dynamic programming method basically by using subproblems will work in this case, clearly will work in this case. So the recursive formulation of the dynamic programming of this dynamic programming thing goes like this. To formulate it recursively, I would ask what happens when you go from k to k plus 1, k minus 1 to k, the inductive step, right? So the two cases. First case is either when I go from k minus 1 to k, either the path that I found with k minus 1 edges was already the best path, okay, already the shortest path, or that was not the shortest path, but when I used another edge, which means I have k edges now, when I used another edge, I found a new path which went through another node u, right, which is got that path to that node u is k minus 1 edges, and then from u I came to this node t with one edge, so therefore this path has k edges now, okay, but this new path has a length, total length, which is total weight, which is less than the edge, shortest path that I found with k minus 1 edges. So there are two possible conditions, either the k minus 1 edges were already optimal, subproblem k minus 1 already found you the best solution to t, or else it was not the best, but when I went from k minus 1 to k, I improved it. How did I improve it? I found a node u to which there is a k minus 1 path, and then from u I came to this particular t, and this path improved it, okay. So either improved it or I did not improve it. So that is what, those are the two conditions. So based on that, I can write the recursive algorithm very simply. So the shortest path STK, recursive representation, shortest path from S to T, K means what? With at most k edges, with at most k edges, right? Remember, we are writing dynamic programming. Shortest path from S to T with at most k edges. If k is equal to 0, then it's very clear, then S has to be equal to T, so return 0, right? Finished. That's the base case. Otherwise, find the shortest path with k minus 1 edges. How do I do that? Call SP again with k minus 1, recursive call. Let M be the shortest path with k minus 1 edges. Two possible conditions exist. One, I already found the shortest path, which means M is the shortest path, so I am done, or I can improve it. How can I improve it? I can improve it by looking at nodes, like say I have a node called W, right? Maybe okay. So here I have used W. It's good idea not to have used W because you can confuse W with weight. All right. W is not weight. W is a node. Okay. For weight, I mean this one at least I have written weight as weight. So forgive me for writing W here. I should have written X or something. Okay. But W is a node here. So for all, so there is a node called W, which basically from S there is a path of length k minus 1 to W. Therefore, for that particular thing, SP SW k minus 1 is the best path, isn't it? Because it's path k minus 1 to W, and then add to it the weight of WT, and that particular SW k minus 1 is the shortest path of k minus 1 edges to W. Add to it the weight of WT. That will be a new path that I have found, which is of length k, which has k edges, and that path, if it is got a weight which is lesser than M, right, then M will become changed. If it is not lesser than M, M remains the thing. So either after this step M is not changed, which means basically already found the shortest path in k minus 1 steps, k minus 1 edges, or it improved it, which means M became less, which means it improved it how? Where I found via another vertex W, I found a better path. Okay. So very simple, again you can see this dynamic programming, very simple recursive algorithm written in one page, right, written in one page using recursion, and what I have done here basically is I found out the shortest path using Bellman fold. You can also write the same algorithm bottom up instead of writing it top down or recursively. Every recursive program, dynamic programming program can be written bottom up, but you have to be very careful to write it bottom up. So it's clear that I am doing, what am I doing? I am maintaining the shortest path between S and T with K edges. That's what I am maintaining. So, so I can keep an array called OTK because I am always starting at S. That's why I am not writing STK. I could have written OSTK, which means 3-dimensional array. I don't need, okay, because I am starting from S. Therefore, I am not keeping it. So I keep an array called OTK, and this array keeps the shortest path that has been found so far to T with at most K edges. Okay. So OSK is equal to 0 for all K and OT0 is equal to, I should have written infinity here. I think that symbol vanished because of something, right? This is infinity for all T. Okay. And then I do what I do basically is for every K 1 to N, I look at whether or not, so here I have written V, right? So I look at neighbors, I look at nodes V and then I try to see whether I can improve it by going via V. So to go via V, what I have to do is I have to look at the shortest path of a K minus 1 edges to V and add the edge of the edge from V to T, right? Weight of V to T. So either basically I have already found the optimum in K minus 1 edges, which is OTK minus 1, or I am going to improve it by using one more edge, right? I am going to improve it. How am I going to improve it? I am going to go through a vertex V and I am going to improve it. So this basically, this step is going to written with just no recursion at all. There is no recursion in this. Only thing all I am doing basically is I am going from K equal to 1 to N. I am starting from K equal to 1 so that when I do the Kth step, I am calling the K minus 1 step, and I have already done the K minus 1 step in the earlier iteration of this. Okay. So the whatever recursion was doing, which was calling K minus 1, I am doing by iteration here, but I am making sure that I am doing the iteration in the correct order, right? The earlier step is done first and then the later step is done. Okay. So similar to Fibonacci, right? I can write Fibonacci using recursion. I can say Fibonacci of n, call Fibonacci of n minus 1, call Fibonacci of n minus 2, add the two results, return it. This can be one way. The other way is that I can keep an array called fib k, fib of n. I keep an array, okay, and I can start from 0, calculate the Fibonacci of 0, set it as 1, calculate the Fibonacci of 1, set it as 1, calculate the Fibonacci of 2 by adding 0 and 1, calculate the Fibonacci of 3 by adding 1 and 2, 4 by adding 2 and 3 and so on. So this is the iterative way of doing Fibonacci. The same way you are doing here bottom up, okay. So this is a bottom up way of doing Bellman-Ford. So you can see that from the bottom up you can calculate the complexity easily. There are overall n steps because you are doing K equal to 1 to n. So there are n steps, and in each of these steps you are actually looking at potentially all the edges. That's why you are doing order m potential steps. So in the worst case you may do order m times n in Bellman-Ford. Remember that the Dijkstra's algorithm found the solution in order m plus n log n. If m were order n log n, whereas this is doing order m times n. So if m were basically of order n of the size of n, you are doing order n square. If m were of the size of n square, this is taking order n cube time. Bellman-Ford is taking order n cube time. Okay, so it's not a very efficient algorithm. Of course, you can improve Bellman-Ford also by using some interesting data structures, but we don't have time to discuss in today's class. But it works for graphs with negative edges, right? So when you have graphs with negative edges, or when you have graphs with edges whose weights basically you don't know whether it's going to be positive or negative, you cannot use Dijkstra. You have to use Bellman-Ford. So it might take a little bit more time, but you're sure the answer is correct, isn't it? You can use Dijkstra, but the answer will not be correct. This is why I explained you have to first make sure your algorithm is correct. Then you check for complex. Don't try to go for cheap algorithms. They may give you wrong answer. Okay. You don't want cheap fast algorithms which give you wrong answers. You want algorithms which are right. Then after that you look for whether or not the algorithm is right. Okay. So the interesting thing about Bellman-Ford is that it can also find negative cycles. What are negative cycles? If I go around a cycle, the weight of the cumulative weight of that is basically negative. Such a thing is called negative cycle. Okay. How do I find a graph with negative cycles? I find after the algorithm has stopped, which means after it has finished, I check whether or not there is a node V, right, such that order Vn plus weight of Vt less than order Tn. If there is a pair, if there is an edge Vt such that order Vn plus weight of Vt is less than order Tn, there must be a negative cycle. Strictly speaking, we cannot stop Bellman-Ford. We stop Bellman-Ford. Bellman-Ford would have tried to improve because it was said, okay, through V I found a better path. So I should improve it. Even after n steps, I have not been able to find the best path, I can improve it. Even after n steps, if you can improve it, it basically means that there is a cycle in the graph, negative cycle in the graph. Is that okay? So not only does Bellman-Ford find you the optimal solution for a graph which has no negative cycles, but also Bellman-Ford, if at all the graph has negative cycles, it will tell you it has negative cycles, and so you know whether your graph has got negative cycles. Okay. Now I am going to show you very quickly a interesting application of these graphs with negative cycles and so on in what is called constraint satisfaction. Typically, a constraint you get, and a simple difference constraint is a constraint where you have a variable xi and a variable x. You have a set of variables x1 to xn which can mean something, like for example xi could represent the time at which you should execute a specific instruction in a processor, for example, okay, and you are saying that I should execute this instruction only after another instruction. So you will say xi is less than or equal to xj. Xi is the time of executing the ith instruction, xj is the time of executing jth instruction. It is saying j should be executed after I, so xi less than or equal to xj. Then you are saying this happens in a processor which can issue many instructions and do all kinds of crazy things. Then you are saying maybe you want to say not only should I have xi done, xj done after xi, but I want xj to be done after xi and a gap, small gap, 3, a gap of 3 should be there between xi and xj. So which means xi plus 3 less than or equal to xj. Okay. So such kinds of constraints are called difference constraints. So xi minus xj less than or equal to cij. The cij can be any number, real number. Okay. It's used in compilers, used in VLSI architecture design, used in many places. Okay, such kind of different constraints. So here is an example. So I'm saying x1 less than or equal to x2 plus 2, x2 plus 3 less than or equal to x3, x3 less than or equal to x1 plus 1. You can see this is cyclic, right? So I've written x1 in terms of x2, x2 in terms of x3, x3 in terms of x1. And I can try to write it in standard form. x1 minus x2 less than or equal to 2, x2 minus x3 less than or equal to minus 3. So I put 3 on that side, 3 on x3 on this side, like this. I am asking myself, can I solve these constraints? The answer is these constraints can be solved. I mean, of course, I can solve these constraints by trying to do some complex geometry thing, all right, which is what in linear programming and all you try to do. See whether this represents some convex region, and I want to see whether this convex region basically is empty or not empty, right? If it is not empty, then it basically means that I can solve this constraint. I can do that, but that's a very complex algorithm. Okay, a much simpler linear time algorithm, almost linear time algorithm, can be done by using these graphs. Okay, constraint graphs. How do I construct such a graph? What I do basically is that I write for every xi, I write a node. So x1 I wrote one node 1, x2 I write a node 2, x3 I wrote the node 3. And whenever I see x1 minus x2 less than or equal to 2, I draw an arc from 2 to 1, not from 1 to 2, from 2 to 1, and label it with this value, which is 2. So x3 minus x1 less than or equal to 1, so I draw an arc from 1 to 3 and label it 1. x2 minus x3 less than or equal to minus 3, so I draw an arc from 3 to 2, label it minus 3. So I draw this graph like this. This graph has cycles, but you can see that it has no negative cycles, because if you add 1 plus 2, 3, minus 3, 0. So no negative cycles in this graph. And because it has no negative cycles, this graph has no negative cycles, I must be able to use Bellman-Ford to find shortest path in this graph. Okay, basically. Now what I do is, in this graph, I add another node which is called 0, and then I connect 0 to all the other nodes and put edges with weight 0 on it. Okay, like this. And then I run Bellman-Ford starting from 0 to all the nodes and try to find the shortest path. Okay. Now see the meaning of this. Suppose I read x1 as the distance or the length of the shortest path to node 1. I read x2 as the distance or the length of the shortest path to node 2, from 0, of course, right? We are starting from 0. Then what is x1 less than or equal to x2 plus 2? What does it say? It says basically that the shortest path to node 1 has a distance which is less than or equal to shortest path to node 2 plus 2, right? Shortest path to node 1, that's what this is saying. Shortest path to node 1 is less than or equal to 2 plus the shortest path to node 2. But you can see here in this diagram, shortest path to node 1, I can find some shortest path to node 1, or I can go via 2. I can go to 2 and then take this 2 and come to 1. So shortest path to node 1 is less than equal to the shortest path via 2. Clearly, shortest path to node 1 has to always be less than equal to the shortest path via 2, right. Shortest path via 2 basically is the shortest 2 plus 2, which is why the shortest path to 1 is less than equal to shortest path to 2. Therefore, I can read this very clearly as read xi as shortest path from 0 to node I, and then all these constraints will just be represented with this graph, completely represented this graph, and therefore I can use Bellman-Ford. Is it okay? I can use Bellman-Ford from 0 to all the nodes, and if Bellman-Ford finds me a shortest path, then that shortest path is the answer for that particular constraint. So I use Bellman-Ford and I found x1 equal to -1, x2 equal to -3, x3 equal to 0, and so I have solved these constraints. You can check for yourself that these constraints are solved. -1 minus of -3, so 3 minus 1 is 2, it's basically equal to 2. x2 is -3 minus of -1, so -3 plus 1 is -2, which is less than equal to -3, and so on, right. So you can see all these constraints are satisfied, alright. Here is the problem that I am going to leave for you as an exercise. I give you a bunch of constraints like this, write it as a graph, so run Bellman-Ford on it, find the answer, okay. This exercise, homework for you, homework, okay. You are not going to do it. The last thing I am going to discuss in class before we get into problem solving, right, to the last half an hour, 40 minutes I want to do problem solving, and also take questions from you, is minimum spanning trees, MST, okay, minimum spanning tree. Now many problems that we face, basically we are not looking for shortest path, right. So shortest path means I have given a source node S, single source shortest path means I have a source node S, from that source node I am trying to find the shortest path to all the nodes. Many times I am not saying find the shortest path from a given node to another node or something. I am saying find me the least cost way of connecting a bunch of nodes. I have a set of nodes, find me the least cost way of connecting these nodes together, right. I want to make these nodes connected. How do I connect these bunch of nodes? Imagine, for example, I have a board which I am making, printed circuit board I am making, I have placed all components on the printed circuit board, I am trying to make a ground plane. You know, ground plane will basically visit all the nodes, right. Mostly in an electric circuit, all the circuits, all the ICs that we place on the board are after all to be visited, they all will be connected by ground. So I have to visit all the elements. So what is the least cost way of visiting all the things that are placed on this board? Okay, so this is one of the problems. This is called, so this problem is called minimum spanning tree problem. Given a set of locations V1 to Vn, we want to connect all these locations with a network. So imagine, for example, I have a number of cities in India and I want to lay India, they are talking about national optical fiber network. I want to collect all the villages in India. What is the least cost way of connecting all the villages in India via fiber network? Okay, what is the least cost way of making sure that every village in India is connected by fiber? So we have a set of locations V1 to Vn, they are villages, let us say. We want to connect all these locations with a network. CVI Vj is the cost of laying a line between Vi and Vj. Okay, for every pair of nodes I can ask myself the hypothetical question. I am not laying the line, I am just asking the question. If I want to connect Vi to Vj, how much money I should spend? Okay, so I can go to one village, next village, and I can lay a fiber between one village and the neighbor village. Then how much it will cost me? Vi Vj. See Vi Vj, cost of laying link between Vi. It's not that means that I'm not laying the network and then asking question. I'm asking before I'm laying. It's a planning problem. Okay, so that means this graph, this planning graph is a complete graph. All edges are there, and every edge has a cost, which is C Vi Vj. Now the minimum spanning tree MST basically is a subset T of E, which means I have the complete graph. I want to take a subset of the edges of the graph such that firstly Vt is connected. I want to connect all the nodes, right? So Vt has to be connected, and such that the cost of the edges in T, if you add up, that will be minimum. The least cost way of connecting all the vertices. Okay, least cost way of connecting all the vertices. Now clearly, I'm not written that T is a tree, by the way. I'm not written that T is a tree, but clearly T is a tree, because if T were not a tree, which means that it has a cycle, then one of those edges in the cycle can be removed. It will still be connected, and the cost will come down, isn't it? Because all the costs are positive, right? All costs are positive. I have not written it. I have written it here. All costs are positive. So if I have a cycle, if I remove one of the edges, then the cost, the thing is still connected and I have reduced the cost. So therefore, it is going to be a tree. I do not have to say tree, it will become a tree automatically because of that condition. So there are three different kinds of algorithms that you can consider for constructing the minimum spanning tree. Okay. The first algorithm is a very simple algorithm, it is called Kruskal algorithm after Kruskal. All invented in the 50s and 60s, all these algorithms are very old, okay, they are very old algorithm. So what does it do? It starts with an empty set of edges. This is not working on nodes. So far all our algorithms worked on nodes. These algorithms work on edges. The minimum spanning tree is working on edges. It starts with an empty set of edges and it adds one edge at a time. Which edge it will add? It will add the edge with the least cost. It will sort all the edges by cost and say, let me add the edge with the least cost. Okay. So start with empty set of edges, take the edge with the least cost, add it, take the edge with the least cost, add it, keep on adding like this. When do you not add an edge? If you add an edge and it turns out that that edge causes a cycle along with all the edges that you already added, then you don't add this edge. Okay. So scan the edges in increasing order of cost, keep on adding edges. When you find that adding an edge creates a cycle, don't add that edge. It doesn't cause a cycle, add it. If it does cause a cycle, don't add it. Do that, go on doing that till you exhaust all the edges, and at the end of it you got a connected graph which is a tree and which has a minimum cost. Very greedy algorithm, simple greedy algorithm which is just constructing the tree by adding edges, and this is called Kruskal's algorithm. Okay. Second algorithm called Prim's algorithm. The way it works basically is similar to Dijkstra. It says start with any node. Let's say we start with a node S. Because it's connected, it doesn't matter which node you are going to start with. So let's say we start with any node, call it S, and use like Dijkstra, use a greedy algorithm, but rather than picking the vertex J which has the minimum distance written on it, that's what you do in Dijkstra's. Right now we are going to pick the vertex J which has the minimum attachment cost. What is the attachment cost? The cost of Cij such that I is in S and J is not in S is minimum. The cost of attaching vertex J to the list, to the tree which you have constructed so far. It's not a tree, it's a forest. It will become a tree only at the end. It may be a forest. Okay. So whatever I have constructed so far, adding the vertex, right, J to it, J to this list of S which I have already constructed so far is minimum. So the least attached cost, right. So I am not finding the least distance because least distance basically means that I am taking a path, right, and then calculating the distance. I am not looking at distance like that because I want to calculate the shortest tree. I want to make the minimum tree. I am not finding the minimum distance or something. Okay. So that's why I am taking the minimum attachment cost. So use Dijkstra like algorithm, but rather than distance, use attachment cost as the metric. The third algorithm is called backward Kruskal. It's like Kruskal's algorithm, but it works backward. Start with all the edges and remove edges one by one. So which edge you will remove? Clearly you want to remove the edge which has the highest cost. So you go in inverse order of it. Take the highest cost edge and throw it out. Keep throwing out an edge. When will you stop throwing out edges? You stop throwing out edges when you throw out the edge it becomes disconnected. If throwing out an edge makes the graph disconnected, don't throw out the edge. Keep throwing out edges which are in decreasing order of cost, and if you find the edges, removing the edges making it disconnected, don't discard it. Okay. Like this you keep coming down from highest weight to lowest weight, and you stop when all the edges have been examined, and then that algorithm will also return a tree, and that tree will have minimum cost, and it's called backward Kruskal. Okay. All these algorithms are optimal, but I'm not going to be able to prove to you that they are optimal because we don't have enough time. Okay. Now why does Kruskal's algorithm work? And the reason why Kruskal's algorithm works basically is at any given point in time, what is Kruskal's algorithm doing? We have, just like in Dijkstra's algorithm, we have a set of visited vertices, a set of unvisited vertices. We are constructing a set of, we have collected a set of edges, right? S. So you're basically, if you take any given node U, so you have set of S, right? If you take any, what is a, okay, I'm going to discuss something called cut property, which in the Thursday's class when we discuss network flow, this will become a lot more detailed, we'll be discussing it. But if S is a subset of V, right, let S be a set of vertices. So you are dividing the vertices into two sets. Visited and not visited is what we did there. Here we are saying let us say S be any set and V minus S is the other set. Okay. So consider all the edges that go across the boundary between S and outside S. So these are the edges which are crossing the boundary. That set of edges is called a cut. Okay, called a cut. So X is the cut. Set of edges which are crossing the boundary between S and the rest of S, rest of the. From the cut X, I can pick the cost HE, which has got the minimum cost. Let's say E is the minimum cost. I can pick that edge. Now for any cut means any way of breaking the list of vertices into two halves and looking at the edges which are crossing the boundary, right? That's called a cut. I can pick from that cut the edge. So remember, the cut is basically a set of edges. I'm picking from the cut the edge which has the minimum weight. Let's say E is the edge which has the minimum weight. I claim that E will belong to every minimum spanning tree. E will belong to every minimum spanning tree. Why is that? E will belong to every minimum spanning tree because assume for a moment E did not belong to a minimum spanning tree. Then E is connecting two nodes V and W. Now there is a minimum spanning tree which I have constructed, right? E does not belong to it, right? In that minimum spanning tree, V and W has to be connected because every node is connected, every node in a minimum spanning tree. So how is it connected? So there is a path from V to W which is not going through E because E is not there in the minimum spanning tree. So that path will go through U, let's say V prime, W prime, X, and then come to W. So it will go through nodes inside S, then it will come outside S, then it will join to W. So somewhere that path which is connecting V to W has to cross the boundary between S and outside of S, and that place where it's crossing the boundary, let's say V prime. Okay. So we are relying on the fact that we have found a minimum spanning tree. Assume for a moment that E, which is the least cost edge, is not there in that. Then you are basically saying that there should be a path from V to W that goes from V to W, and it has to cross the boundary because your V is inside, W is outside. So it has to cross the boundary somewhere. Let's say it crosses the boundary at E prime. Now because E is the least cost edge among all the edges that crosses the boundary, therefore E prime has a weight which is larger than E, isn't it? So if E prime has a weight which is larger than E, then if I replace E prime by E, then I will get another minimum spanning tree. Minimum spanning trees have a very interesting structure which allows you to exchange edges like this. Okay, so I can't get into now, but it has a very interesting matroid property which you can basically exchange edges. So I can drop E prime and add E. If I drop E prime and add E, I will not make cycles. There will be no cycles, and this will also be a tree. Okay, and this will also be a minimum spanning tree. This will also be a spanning tree, and this will be having a total weight which is less because E prime has a higher weight than E. So dropping E prime and adding E basically will reduce the weight of the tree, which is a contradiction because I said earlier that E is not part of the MST and E prime is part of an MST, right? It is a minimum spanning tree. So it's a contradiction. Therefore, E has to belong to every minimum spanning tree. Okay. So I know this proof I went through not fast, but you know all proofs of this kind are contradiction. Use contradiction in one way or the other, and contradiction proofs are very hard to understand. I mean that's the problem. One way to think about it is that you have to include E in the MST because if you did not include E, then you will have to include E prime which has a higher weight, and that can't then be an MST because it will have a higher weight than the MST which contains E. So therefore E lies in every MST. Okay, because E lies in every MST, therefore Kruskal's algorithm will work. Because what is Kruskal's algorithm doing? At any given point in time is collected a set of edges. It is taking out of the edges that have not been collected so far, it is taking that edge with the least cost. So that edge basically it's picking E, and we know that E belongs to every MST. Therefore Kruskal will actually build an MST. Okay, that's all I wanted to do in today's class. Now what I will do now is I am going to show you a list of problems. Okay, we are going to go into a mode where I speak less and I let you work on problems, and you are going to work in groups. If you want to work individually you can, if you want to work in groups you can work in groups, whichever way you want you can work. I am going to give you from one problem at a time. We are going to do maybe 5 minutes for the problem, okay, because then we can do maybe 5 or 6 problems. I have 7, okay, maybe 5 to 10 minutes. Okay, you will discuss in your group, you will find a solution. This problem is very simple. you will discuss in your group, you will find a solution, and whoever has found a solution will raise hand on the system, and then you will tell me your answer, problem solution, and I will write the problem solution on the board here. This is how we are going to do. Okay, so that way you have a chance to participate in problem solving. You have a chance to participate in problem solving, and 2 or 3 of these problems we have discussed earlier already. So I am going to start with them, but then I will quickly move to a problem which we have not looked at, so that it's a little bit more interesting. Otherwise, we are discussing same material again and again. It may get boring. First problem. I hope you thought about this. I presented this problem yesterday's class. Okay, we said that a cut vertex is a vertex. It's also called articulation point. Cut vertex is a vertex that if I remove from the graph becomes disconnected. Cut vertex is a vertex that I remove from the graph becomes disconnected. How can I use DFS, or if you want to use BFS, whatever it is you want to use, how can I use graph traversal to find all the cut vertices in a graph? Problem is clear? Problem is clear? Is the problem clear? How can I use graph traversal to find all the cut vertices in a graph? You got to use basically, let's say you are using DFS, you know that in DFS you will visit nodes, you will maintain pre and post counters, and you can use low counters or any other counters. You can even add more counters if you want. Using these counters, you have to somehow find out whether a vertex is a cut vertex or not. In the last class, I discussed how to find out whether a vertex is, an edge is a cut edge or not. What did I say? Maintain low value of counter, low counter, right? If you find a vertex whose low value is equal to its pre value, then that edge is a entry point into a cluster. So the parent of that node, the edge connecting the parent of that node and this node must be an edge which is a cut edge. We said that. Okay, so that is a clue in some sense, right? Now just to make your problem a little bit more difficult, let me point out that cut vertices, cut edges will always, if this is a cut edge, then this is a cut edge, then this is a cut vertex, this also is a cut vertex, both of these are cut vertices. Okay, both of these are cut vertices. I hope you can see what is written on the board, right? But that need not be the case. Need not be the case. Here I am giving you another graph like this. Here this graph has no cut edges. This graph has no cut edges, but this vertex is a cut vertex. This is a cut vertex because if I remove this vertex, the graph will break down into 2 pieces, right? This piece and this piece will get disconnected. Okay, so you have 5 minutes, work in groups, and whoever finds the solution will put up, raise hand, and we will discuss solution. Okay, what is your method of finding cut vertices in a graph? How do you find cut vertices in a graph? Okay, you can work on the problem. I mean, you don't have to look at me now. Just work on the problem and discuss with your friends, neighbors, whatever it is you want to do, you can do. You can raise hand, and whoever has raised hand, I will give you a chance to present your solution. Okay, we can write the solutions on the board. Okay, so we should have answers by now. So do we have any answers from anybody? Okay, so if somebody has an answer, then you can either come online and give me your solution. So what is your solution? How do you find out the cut vertices in a graph? So we figured out that you can cut something is a cut edge if you visit the do a DFS of the graph, find out the low values for all the nodes. The low value is equal to the pre value. Then the parent of that node to that node forms a cut edge. So GEC college, GEC, can you hear me? I have an answer in chat as well. So GEC.
Sir, we come to the conclusion that if we select each node and delete that from the set of nodes and perform a DFS and check whether the visited array, each element of the visited array is 1, we can find whether that the deletion of that vertex caused a disconnection in the graph.
Okay, so that is one way of doing it, BFS or DFS. So you delete the node, construct a graph, and then find out whether the graph is disconnected. If it is disconnected, then basically it has to be a cut vertex. Now the problem with that is that how many times we will have to repeat this algorithm? You have to do it for every node, right? So you are doing order m plus n log n for the traversal. You're doing, I'm sorry, you're doing order m plus n operations for doing a graph traversal, and you're repeating this n times. You're doing order n into m plus n. So order nm is your complexity, but it will work. Okay, this is one solution. It works. It's high complex, somewhat high complexity, but at least it works. All right. So good, very good, excellent. Now let me look at what are the answers that have come on chat. Okay, the first solution which has come from VP College, VPCV. For finding cut vertex, we can find cliques, complete subgraph, then find vertex which is common in cliques. That is, vertex will be cut. That vertex will be cut vertex. Because of the diagram I have drawn here, they have gone to cliques because they think that the triangle is a clique and so on. And but that may not be the case. Vertex will be a cut vertex for given example. So in this particular example, maybe that is the case, but clearly, you know, that is not going to be a solution, because I can make this is a clique and I can make another clique. This is another clique. These are two cliques. This is one clique. This is another clique. So I can have two cliques, right? You can have two cliques which are shown here. This is one clique. This is the other clique. I can have two cliques and they are sharing common vertices, but neither of those vertices is a cut vertex. Alright, so that what you have presented here is okay for the diagram that I have shown here, but is not in general a solution, alright, for finding cut vertex. Okay, so DCE has given the solution. If visited I for a node has been set to 1 and we are reaching that node again, it means it was reachable from two different positions. So we can remove that node. No, but that doesn't mean that it's a cut vertex. It only means that that node is reachable in two different ways. So it may be participating in a cycle, but that, so nodes which are parts of cycles are not cut vertices in fact. So it doesn't say anything actually. So we don't know. That is not necessarily a solution. All right. Now we have another solution from VP COE. Vertex common in these two cliques. Okay. So again he is looking at cliques. So how do you find cut vertices? He is saying basically look. People are saying look at cliques. So looking at cliques may not necessarily give you the answer. Okay, may not necessarily give you the answer. Okay, so I am going to suggest a solution for you. When you go back and think about it at home and see whether the solution works. We said basically that something is a cut edge if the low value is equal to the pre value, then the parent of that node and that node must be collected by cut edge. But it also tells you something. See here in this example, 4 1 is a cut edge, 4 is a cut vertex, 1 is a cut vertex, 9 10 is a cut edge, 9 is a cut vertex. Okay, so it says something that you can, by using the same method, you should be able to find cut vertex also. How do you find cut vertex? If there is a node, so 4 has a low value which is equal to 0 because you can see 9 from 4, right? We go down and you can see 9. So 4 has a low value which is 0, but 1 has a low value which is 7. So if there is a node who has a neighbor whose low value is different from this node, then this node must be a cut vertex. Think about whether that is the case or not. Okay, I am suggesting to you an algorithm. If a node has a low value different from the low value of its descendant, right, of it, any of its neighbors, then that node must be a cut vertex. In this case 4 for example is a node whose low value is different from that of 1, and therefore 4 must be cut vertex. 9 has a low value which is different from that of 10. Low value of 10 is different from low value of 9, therefore 9 must be a cut vertex. So any node whose low value is different from the low value of its neighbor must be a cut vertex. I am suggesting to you that this may be a method, okay, but I am not telling you whether it is right or not. Please check it out yourself for yourself whether this method works. Alright, now I am going to go to the second problem. Okay, maybe before I go to this problem, I will give you something that is somewhat easier problem and more practical problem. Okay, here is a problem, kind of real life problem, right? There are n currencies like you have rupee, dollar, yen, euro, and all that. So these are n currencies 1, 2, 1, 2, 3, 4 like that to n. The currency trader can exchange a fixed quantity of money from one currency to another. He can convert rupee to dollar. So if you convert rupee to dollar, you will get how many dollars? 1 rupee is giving you today, I don't know, $1 is 60, every day it keeps changing. 67 rupees I think it is now. So 1 rupee will give you 1 by $67. Okay, 1 by $67. So Rij is 1 by 67. I can convert dollar to euro. So $1 is I think 1 by 1 euro is $1.13 something, I don't know. So 1 by 1.13 euros you will get. I can convert euro to yen. So 1 euro might be 100 yen. I don't know how much it is, but let's say it's 100 yen. So I'll get some yen. Then I can convert yen back into rupees. Okay, so 1 yen might be some number of rupees. So I can convert back into rupees. So I can go around like this. I can take a node, convert into another currency like this. Each edge is a current conversion. And if I come back to the same node, I get a cycle. Okay. Now if I start from rupee, go around and come back to rupee, and if I make money by doing that, then basically if I start from a rupee, go around and come back to rupee, then I have a cycle which I made, and if that cycle turns out to have a positive weight, that cycle turns out to have positive weight, positive overall, positive not positive, it has a total overall product. So when I converted rupee to dollar, I got 1 by 67, converted into something, I got 1 by 1.13, 1 by 67 to 1 by 1.13 into, and so on, I keep multiplying. So I go around and I get a number which is larger than 1. And what happened? I started with 1 rupee, I went around and came back and I got 1.2 rupees. Possible, right? This is called an opportunity cycle. In fact, there are people who have made money just doing this. Okay, there are people who have made money just by converting one currency to another and come back to the original currency, made money. Okay, possible to do. So whenever you find that you can do currency cycle like this and make money, you want to do it. You want to do this cycle. Okay, you want to execute this cycle and make money. So write an algorithm to detect if you can make money by converting currency. Is it clear problem? Nodes are currencies, edges are conversions. I want to find if there is an opportunity cycle. Okay, I want to find if there is an opportunity. What algorithm will I use? This is simple. I don't even think you need 5 minutes, but anyway, you have time. I'll give you maybe 2 or 3 minutes. Whoever has answer first, please raise hand, or you can write in chat. What is your answer? So somebody is asking the question, what is the difference between Dijkstra's algorithm and Kruskal algorithm? Difference is that Dijkstra is finding shortest path, whereas Kruskal is finding minimum spanning tree. Kruskal's algorithm is used for MST. Okay, so when you are trying to find not the shortest path between two nodes, but you are trying to find a minimum cost tree that connects a bunch of nodes, then you will use Kruskal's algorithm. Right. So whereas when you're trying to find the shortest path between a pair of nodes, that time you use Dijkstra's algorithm. Okay, so if you are finding this problem a bit difficult to think about, I think I'll give you time to think about it at leisure, right? Think about it at your own leisure, because this is an interesting problem. You might want to spend more time on it. Okay, as I give you the answer and then you lose interest in trying to solve problems like this. Okay, feel free to post questions on this later on also. We have a forum, so you can post questions on this. If you have suggestions, solutions and all, post it and I will answer. Okay, after these lectures, end of these lectures doesn't mean we stop interacting. I can continue to interact with you afterwards also. So I am going to leave this problem with you, right, because it might be interesting. You might want to think about this problem a little bit more, okay, and see whether you have an interesting solution for this problem. Okay, let me go to another problem. Okay, before that, let me tell you a few things, easy things. Can you show that if the DFS tree and the BFS tree are exactly the same, the DFS tree and the BFS tree are exactly the same, then the graph must be a tree. Remember, the DFS tree is the tree found by the DFS algorithm, search traversal. BFS tree is the tree found by the BFS traversal. if the DFS and the BFS tree are exactly the same tree, both of them found the same tree, then the graph itself must be this tree. Okay, so it looks like we need to give you a bit more time to solve this kind of problems. All right. So what I'm going to do is I'm going to just present all these problems to you. Right. All the problems I'm going to present to you now. We have Thursday's class. So please think about solutions to these problems between today and Thursday. If you want to ask clarification questions on these problems, do that now. And Thursday, before I start on network flow, I'll spend maybe 20-30 minutes where all these problem solutions we can discuss. Does that make sense? So you have enough time to think about these problems at home, okay? And work with your friends. I give you enough time. We are not trying to rush you through the problem solving in 5 or 10 minutes. Okay, so here is one problem which you are thinking about how to do. Here is another question, right? Similar question. I give you a minimum spanning tree, MST, and I give you an edge, E. One edge I give you. You have to tell me whether, I mean, I'm not giving you an MST, I'm sorry. I'm giving you a specific edge in a graph and I'm asking you a question. Does E belong to any MST? Does E belong to any MST or not? Which means the algorithm should return true if E belongs to any MST. Otherwise, the algorithm should return false. When it returns false, it will return false if E does not belong to any MST at all. None of the MSTs it belongs to. Right? Now, if you remember that cut algorithm, I showed you that the minimum cost edge that cuts the boundary will belong to all the MSTs. Then I am asking the opposite question. So E returns false if it is not part of any MST. This is the opposite, right? There we found an edge which belongs to every MST because it's the lowest cost edge that crosses the boundary. It has to belong to every MST. Here I am asking E does not belong to any MST. It's opposite, okay? What is an algorithm which if I give you an edge will tell me whether or not E belongs to any MST or not? Okay, this is another problem. We'll discuss all these problems on Thursday's class. Okay, first 20 minutes of Thursday's class. Constraint solving. This one. Now here is another problem. What is a method by which you can find all the strongly connected components of a directed graph using depth first search? What counters will you keep? What values of counters you will use, or what method you will use in addition to counters to find out all the strongly connected components of a directed graph. Okay. So here are your questions. This question we have already discussed, right? I told you the answer for this already. Second question, find all the strongly connected components of a directed graph. Third question, solve the set of constraints by using Bellman-Ford algorithm. Fourth question, if DFS is equal to BFS, this DFS tree is the same as the BFS tree, show that the graph itself must be a tree. Fourth, next question, given an edge, find out whether that edge belongs to any MST. If it does not belong to any MST, return false. If it belongs to at least one MST, return true. Currency trading, we discussed only the problem, we didn't discuss solution. Okay. So we have run out of time. If you have any questions, I can take one question maybe for today. Otherwise, we will visit all these solutions on Thursday morning. You have enough time to work out these problems with your friends. Work out the problems, think about these problems. These are all interesting problems that you can think about. Problems in algorithms are not very difficult, it's just a way of thinking, alright. You got to learn how to think in a certain way, then you get all solutions in algorithms. Very simple once you know how to think correctly. Okay, if not, see you all on Thursday morning. Please come with worked answers to solutions so that I can spend the first 20 minutes interacting with all of you, alright. Okay, thank you.